Welcome to the solutions to the AP Physics Momentum and Impulse Practice Test. So for problem number 1, we have this graph, position versus time, and it said students conducted a conservation of momentum lab. And so they wanted to verify the law of conservation of momentum, so they used two carts, a white cart with these dots and a black cart with these dots. They used video analysis, and this is the graph we get. Now, our question tells us to write a paragraph, so your answer should be in a paragraph. I will go over what should be in your paragraph, but we are going to not just write sentences in our paragraph, we will also have equations and calculations, but those are not enough to explain the answer to this. So you need both words and equations to properly do this problem justice. So our question in part A, is momentum conserved in this collision? So to figure out if momentum is conserved, we look at this and we have two different objects, a black cart and a white cart, and they're both, they both have graphs that are separate from each other. We'll talk more about that graph in just a second. So the basic outline to figure out, is it conserved? We will have some kind of conservation of momentum experiment. So we're going to verify this law. So the momentum of the first cart and the momentum of the second cart before, is that equal to the momentum of the first cart with its final velocity, the momentum of the second cart with its new final velocity? Are these two equal? And so this is the equation that you're going to use. Now, if you look at this, the masses of the carts are given in the problem, but the velocities are not given here. How can we get the velocities from this graph? So if you look at this graph, this is a position versus time graph. The slope of this kind of graph gives you the velocity. So technically the first point, this equation, writing this equation is technically the fourth point in this problem. But the first point is simply stating the slope equals the velocity. So did you describe that the slope of a velocity time of a position time graph is the velocity of the carts? Somewhere in your paragraph. Second thing you need to do is find the slopes of both carts before and after. So if we look at this, let's look at the white cart. The white cart, the slope from the first, 1 second before the collision. So this is the collision. This is the event that changes their velocities. So if we look at the white cart, the initial velocity when we find the slope is 0. Its position is constant. The slope of this line is 0. Now for the second half, this cart is moving. And so we actually need to find the slope. So if we start at 1 second, so for this 1 second of time, we're going to have the change in y over the change in x. So the rise of this cart, it goes from 5 to 8. So the final is 8, the initial is 5, and it does that over 1 second. And so we get a velocity of the white cart, or a final velocity of the white cart of 3 meters per second. Now let's look at the black cart. I'll do that one over here. So if we look at the black cart, it has an initial velocity that's not 0. So if we calculate the initial velocity, we have a rise of, it goes from 0 to, I guess those are both at like 0.5 meters per second. So, and all of that happens over 1 second. So it's a constant velocity because it's a constant slope over that first second, giving us an initial velocity of 5 meters per second. Now the final velocity of the black cart is different because the slope is different. So to calculate that, if we look at the change in y over the change in x, or the change in position over the change in time, we get a final position of 4 meters. And if we look at that, its initial position was at 5 meters. And all of that happened over that last second. So we have a final velocity of -1 meters per second. This negative is important. It's really important. So this velocity is the only one that is now going backwards. So you had to somehow indicate that it's in a different direction than at the initial velocity. So the second point was stating two of the velocities. And the third point was stating all 4 velocities. So all of those velocities that we just found should be on your paper. The fourth point we already said was writing the appropriate conservation of momentum equation. The last point was actually finding the values for before and after. And so if we kind of take this, let me see if I can move this over. Oops. Move this over here, and we'll try to calculate for number 5 what the final velocity is. So if we come over here, and let me do this in blue, so the mass of the white cart is 0.8 kilograms, and the velocity of the white cart initially, so I'm going to come over here, initially the white cart has a velocity of 0. So we could have just written 0 right here. And this cart is 0.4, and its initial velocity, it actually had a velocity of 5 meters per second before, I think. Yes. And so the white cart, which is our cart 1, is now moving. The white cart's final velocity is 3 meters per second. And the final velocity of the black cart, 0.4, this guy is -1. And so if we do the math, this is 0, this is 2 kilogram meters per second. And on this side, we have 2.4 minus 0.4, which also gives us 2 kilogram meters per second on this side. So the fifth point was finding that both initial and final momentum are 2. You have to show your work. You have to show these calculations. So describing it and showing the work are both part of your answer. And those are the points in this part. So A is worth 5 points. Is this collision elastic or inelastic? So the last 3 points will come from this. So to know if it's elastic or inelastic, we can only know that by looking at the kinetic energies. So if kinetic energy is conserved, it's elastic. If kinetic energy is transformed into some other kind of energy, it's inelastic. So let's go. Let's calculate kinetic energy. So the initial kinetic energy, we're just going to look at both carts. Now, this white cart initially was not moving, so we only have the black cart. And so the initial kinetic energy, to calculate kinetic energy, it's 1/2 mv squared. So for this cart, we have 1/2 times 0.4 times 5 squared. And when we calculate it, we get that the initial kinetic energy is 5 joules. To find the final, if we do both carts, in this case, both carts are moving, and we have the white cart has a velocity of 3, and the black cart has a velocity of -1, and we add them all up and we get a new kinetic energy of 3.8 joules. So the first point is showing or explaining that kinetic energy is used, and to decide elastic or inelastic. The next point, point 7, is actually calculating both kinetic energies. And the last point is coming to the conclusion that since kinetic energy is not conserved, we lost some, it was transformed into some other kind of energy, that it must be an inelastic collision. So now we're on problem 2, where we have a bowling ball dropped onto a trampoline and allowed to bounce 1 time. So looking at this graph, we have a velocity graph, and looking at that, we can kind of see that the bowling ball was falling. This period right here must be the bounce, because the velocity goes from negative to positive. And then it begins falling again. So this part A says, how can this graph be used to determine the acceleration of gravity? So looking at this graph, how do you find acceleration from a velocity time graph? Well, we know the acceleration on a velocity time graph equals the slope. And so you must say that the acceleration equals the slope on this graph. And then we have to find any time period over which it's actually falling. It's under the influence of gravity. And so if you say anything like find the slope over over the 2 intervals where it's falling, so before 0.4, before 0.4 it's falling, and then about here is where it's, you know, in contact with that trampoline. But after 0.6, or is that 0.5? That's 0.5. After 0.5 seconds. So if you said before 0.4 seconds or after 0.5 seconds, find the slope, you have both points to part A. Okay, for parts B and C, again, it tells you you need to explain it and show equations and calculations for a complete answer. So B says, what is the ball's change in momentum as a result of being in contact with the trampoline? So let's go back up to our graph. Let's look at that. Now we already identified this time period as when it's in contact with the trampoline. And so to find the change in momentum, we want the initial and the final momentum, right? It's going to be the final minus the initial momentum. And since the mass isn't changing, we can even say that it's going to be the mass times the change in velocity. So you should somehow describe this and how you're going to get these numbers. So looking at this, we could say something like using the velocity at, I don't know, 0.4 seconds is a good period to use. The velocity of 0.4 seconds is approximately -4. And the velocity at, I don't know, what do we want to say, about here? So the velocity at 5 seconds. And this is when it's in contact with the trampoline. So using both of those, we would find the velocity. Now this velocity looks like it's approximately 3, a little bit maybe more. So you could use 3, or you could use, actually, I'm wrong. This is 2, not 3, right there. So approximately 2.3 or something like that. I'm going to use 2 just to keep it simple. If you use 2.3, if you use a slightly lower number for this, as long as we're pretty close and we can tell the values came from this region, your answer, as long as it's consistent with the numbers you picked, is fine. So I'm going to use 2 for simplification. So using these two velocities, we're given the mass. The change in momentum will be calculated by the mass at 6.8 kilogram bowling ball. And the final velocity, we said, is 2. The initial velocity was approximately 4. And depending on the numbers that you used here, you should get, for part B, an answer of anywhere between like 38 to about 43 kilogram meters per second, depending on the values you chose for the velocities. Now, to look at points for part B, 1 point, so point number 2, if we're going through there, or the third point, is for stating the velocities at the time and indicating that it's in contact between 0.4 and 0.5 seconds. Another point, the next point, is for using those velocities in some kind of change in momentum equation or calculating the initial and final. And then the last point is for a value somewhere in this range. Moving on to part C for the next points. For point 5, what average force is applied to the ball when it's in contact with the trampoline? So to figure that out, we just figured out the change in momentum. How is that related to the force? It's the impulse. So this is probably the easiest way to do this. It is not the only way. You could also calculate using this equation. So this equation is also valid. But using our answer from the previous part and stating that the time is 1 second, and I'm just going to use the average value of about 40 right here. To do this in your sentence, you need to say collision, something like the collision occurs at like 0.4 to 0.5 seconds. So that's how that number, you need to indicate where that number came from. And the last point is finding some kind of force value between, depending on this answer. If I had this answer, I would have 400, but again, somewhere between 380 and 430, it's depending on this answer. And so that is part C. For this part, you would calculate the acceleration from the slope and show your work. Again, the time for your acceleration for that change in velocity will be 1 second, and you would use the mass of the bowling ball. And your answer should also be somewhere in this range. So moving on, so part D, we are looking at that. Student notices that the speed upon leaving the trampoline is less than the speed when it first touched the trampoline, and the student makes two statements. These statements are about a hypothetical situation in which the final and initial velocity would be the same. So the student says if the ball bounced in such a way that the final equals the initial velocity, then momentum would be conserved in this collision. Is this correct or incorrect? And explain your reasoning. Okay, so looking at that, if that would happen, the ball would fall, it would hit the trampoline, and then it would bounce up, same as before. If it had the same initial and final velocity, then momentum would be conserved. And so this is actually incorrect. Okay, why is it incorrect? Even though the speeds are the same, if we calculated momentum before and after, the velocity is not the same. They're going different directions. So this is one way to describe the momentum is actually exactly opposite, the same magnitude, different direction. Or you could say there's some kind of external force, therefore momentum is not conserved. So a couple different ways to explain it. You should have a couple of sentences going on to get full credit there. Okay, and the last final 2 points on part E. If the ball bounced in such a way that the final equals the initial velocity, then the collision would be elastic. Okay. So we're looking at elastic collision. Elastic collision, when you see that, that's code for kinetic energy initially equals the kinetic energy final. So to do that, we would have to look at the kinetic energy. So 1/2 mv squared equals 1/2 mv final squared. And so looking at that, that statement would actually be correct. Okay, why? You could actually just like calculate it and show that if the initial equals the final, this guy um, the kinetic energies are equal. So you're going to say this in words. So if it has the same speed, the kinetic energy must not be lost. Now, if you look at this, and unlike the last one, when you square this velocity, this one's positive, or this one's a negative, this one's positive, that both are positive when they're squared. So we said that this is a scalar thing. It's not a vector quantity for energy. So kinetic energy is conserved. So saying that you didn't lose energy, showing that you didn't lose energy will get you the last 2 points for part B. So thank you for spending time with me doing these corrections. Have a great day.